Hello, my name is Colin Greatwood, and today I'm here to talk to you about a fixed mount base eye calibration between a Festo SBSA Vision Sensor and a UR3e collaborative robot using a Robotique handy gripper kit for pick and place. Here you can see that I have a vision sensor mounted overhead statically, a collaborative robot from UR Robots, and a collaborative gripper and adapter plate from Robotique. First, I'll configure the vision sensor. From SBS Vision Sensor, I'll find and add my sensor at 192.168.1.20. Once I've logged in to the vision sensor, I'll load my job set, a standard job that can be received from Festo by reaching out to your application engineer. I'll optimize my lighting for the room that I'm in. Today I'm just using ambient. Feel free to use your own. And I'll auto set both the working distance and shutter speed. For this calibration, the working distance cannot change once it's set, so either measure it or auto set it accurately. My trigger mode needs to be set to trigger. I will not be using multi-shot or any pre-processing filters. The calibration I'll come back to in a moment, but it's set up for 100mm crosshair. Alignment, I will not be using any alignment. The detector tool, I'll slide my part into the field of view, unlock the contour, and zoom out, reset, and then optimize my pattern using the line cursor and a 50mm size. You can see I'm looking here for the black to white transition from the black part to the white background. I'll quickly highlight the contour. Now that I've included everything I want to, I'll press OK. You can see I'm getting a pretty good image find. I'll lock that contour into place. I might optimize the edge finding a little bit here on contour optimization. The result offset, I'll set back to the 0 defaults for all 6 parameters for Robot 3D. You must select Robot 3D, and then I'll adjust where I want the center of my grip to be. You can see here using the red boxes that I have optimized my pick region based on the gripper finger size, and I'm rotating my center of gravity of that pick region to match that of my pre-configured tool center point on the robot. And obviously based on field of view, I'm only looking for one part. For output, I must enable the Ethernet channel by checking Enable, and my string here is pre-configured using the standard job. I'll share the overall result and pose 3D as part of my Telegram payload. Lastly, I'll remove the part so that I can reveal the 100mm crosshair calibration grid with fiducials below. Because it consumes most of my field of view, I'll use one image. The first thing I'll need to do here is drive down using my base feature so that my closed gripper is just barely hovering over top of fiducial 1. This will help me to set my 4 world coordinates for the calibration. I'll use some precision here to make sure that I get very close to the paper without touching it, and then I'll fine-tune that my tool center point is right on top of fiducial 1. Once I've found the location that I want, I'll look at the tool position shown here, X and Y, with the feature base selected. I'll take that X and Y and type it into world X1, 348.88 or 85, and world Y1. Then I'll repeat this process for positions 2, 3, and 4. I'll jog my tool center point over to fiducial 2 of the paper, take some time to accurately position it over top of the fiducial. Once I feel that it has been accurately positioned over the fiducial, I'll take a look at my tool position with the base feature selected, and I'll type in that X and Y shown in the screen capture here to world X2 and world Y2. Now I'll jog my robot over to the third fiducial. I'll take some time to accurately position my tool center point over fiducial 3. Once positioned, I'll look at my tool position XY here with the base feature selected, and I'll type in the tool position XY to world X3 and world Y3. Lastly, I'll jog to fiducial 4, accurately position my tool center point over fiducial 4. Take a look at my tool position X and Y with base feature selected and type that into world X4, world Y4. Now I have all 4 fiducials input to my calibration. I'll retract my robot out of the way so my camera has a clear view. Click Start Calibration. And you can verify that your calibration was successful by looking at the % field of view coverage and the resolution achieved by your calibration. Lastly, I will save my job to whatever name I want and save my job set. With trigger mode selected, I will start my sensor, and my vision sensor setup is done. Now I'll go to the robot side on the Teach pendant. By clicking the menu icon, going to Settings, System, and Network, I'll set a static IP address of 192.168.1.2 and a subnet mask shown here that's on the same subnet as that of my vision sensor. You can see that my vision sensor from the configuration screen is at 192.168.1.20. Next, I'll change my UR program by loading the sample provided from Festo. Power on my robot. Once it's been powered on, I'll go to the Program tab, input my vision sensor IP address here for SBS Connect, which was .1.20. We can verify that again from the device manager. Next, I'll load my basic script by clicking Edit, Open, navigating to the UR library basic script, saving, and exiting. Next, I'll verify that I've set my mount type to fix, which is all lowercase FIX. If I was hand mounted, I would type ARM, ARM, but this configuration shown is a fixed mount, FIX. Next, for SBS change job, I'll type in JOB1 as shown in my configuration studio, all lowercase. This has to match. Next, I'll teach my image pose, which for this type of calibration, my robot just needs to be out of the way of the camera. Then I'll put my part back into the field of view and teach the gripping pose under the initialization folder. I'll jog my open gripper over to the part, and this is an example of a pick type calibration. I'll use my finger to gently hold the part in place. Once I'm happy that I'm at the gripping position, I'll open and close my gripper to modify the position of the part just ever so slightly, jog the robot out of the way, and then retract out of the field of view of the camera. Without moving the part, I'll let it go. Lastly, I'll modify the approach position for this gripping pose. You can see here that it's going to be not 30 millimeters, but 50 millimeters above my pick position. I'll reset back to 30 millimeters as I want to approach it closely. Lastly, my initialization routine has been all set. I'll run the initialization and now press stop program. This teaches the pick plane for the gripper. Now that my initialization is complete, I'll press stop program. I'll suppress the initialization folder as I don't need it any longer for standard operation. Then I'll scroll down and modify my standard operation approach pose. You can see here I've filled in the rest of the program. Feel free to modify your gripping open or close as you see fit. You may be using vacuum and you need to change how you pick and place the part. For the approach pose, you can see right now I am approaching 50 millimeters above my picked part. I'm going to modify that to be a little closer. I'll change it to 30 millimeters above my picked part. The last piece required for my operation here, assuming I've modified my grippers, is a drop-off or next part of the sequence. Here I'm just going to use a simple one waypoint. I'll retract my robot, jog over to the free space, and you can see I'll just be catching the part here. So I'll set waypoint, drop off, out of the way. Now that my program has been modified and everything's ready to go, my initialization folder must remain suppressed for standard operation. I'll save my program and installation file and then play my program. The camera takes a photo. The robot goes to pick it. To show that it's accurately accounting for change in position, I will translate the part toward the left side of the screen. You can see that the pattern was found and the part picked. Now I'll translate to the right side of the screen. The part was accurately picked. I'll translate my part down and left to the extreme of the field of view. I'll translate it up and left within the field of view. I'm just showing variation. And now I'll show rotation in one direction, and now rotation in the other direction, clockwise and counterclockwise. Thank you for your time.